Welcome to the demonstration movie from FARO Technologies on our newest product, FARO Reality, and focusing on the embedded analytical tools for conservation of momentum, angular and collinear, as well as crush analysis and simulation. All of those are found under the analysis tool in the Reality interface. So these tools allow you to work right on whatever scene you've created in doing the analysis. So whether that's a point cloud, total station points, a Google map, it really doesn't matter. You're going to use the tools as part of the diagram, you might say, or the three-dimensional scene. So what we'll do is we'll start a new scene here. We'll bring in a Google map as a good example. So we'll use this example here, just an intersection in North Carolina. It could be any intersection, doesn't matter. And what we're going to do is choose the part of the intersection that we think would be relevant if it was a real case. Click OK. Now it's in the software precisely to scale. So if we measure, say, from the curb edge over to the edge of the median, that distance of 65.86 feet, that's going to be precisely correct. So the scaling is done to 9 decimal places. All of the imagery here is orthorectified. So what we're going to do now is just lock that layer. We're going to delete the cars. So that's real simple. We could delete all the cars, but for the purposes of this demonstration, we're just going to get the ones out of the middle of the intersection. On a real case, get rid of all of them. If we erase a line, we can always just draw it back in. In this case here, we're not going to do the drawing. We're just going to do momentum. We're going to start with measurements, download. So you can download from point cloud scanner, total stations, data collectors, use hand measurements. You can do absolutely any type of measuring. The list is very, very long of the instruments that we support in a direct way. You don't need any other software. So you can come from the onboard data collector right into the software or the external data collector. So we're going to import it. There's our points, and now we can move the points and align them with Google Earth. So ARIS customers do this a lot. All you need is 2 reference points to do it this way, and then the actual evidence points. Then all you have to do is click the button to join by common description, ZX coding, or any other type of line coding that's out there. Let's change our point size. Now we're ready for the next part, which is let's figure out how fast these cars were going. So we go Analysis, Momentum. So this is linear momentum, sometimes referred to as angular. So there's your momentum system, and it's live. As we're doing it, numbers are changing, things are being calculated in real time. That's what makes it particularly useful. It'll also drive error messaging at certain times. So that first thing we're going to do is go to Vehicles, and we're going to go right to the database of 27,200 vehicles. Choose the vehicles that were actually involved in the crash. This puts them on at the right size and at the right mass. So in this particular case, both vehicles were the same. They were both Caprice Classic cars in this actual crash. So there's one, there's the other one, and you'll notice now they've gone in at their curb weights. You can add in for fuel and cargo, passengers, etc. Now you'll see grips to align the vehicles and their maximum engagement orientation. This car actually went right up here to final rest, as you can see by the points. It rotated twice, so we'll spin this vehicle twice and try to get an agreement between the simulated tire marks and the real ones. And that shows we really need to move this car a little further in that direction. And now we've got a pretty good agreement. We have to put in some interim positions to get it to actually follow the lines precisely, because there's been some uneven deceleration there. But for the first calculations, that's not a problem. And this vehicle did a 180 like that. And this grip here is your damage centroid, your common damage centroid. Place it where you think it should be. At that point, a calculation is performed to determine if they reached a common separation speed. They should theoretically be within 10% of each other. This is the departure grip. So I'm moving it so I can get my simulated tire lines right after impact lined up with my real tire lines, because that's often where momentum mistakes are made. Now we've got a really good agreement on the departure angle, and if we go over here in the left panel for results, we got speeds in whatever units you want to work in. And it doesn't take very much time to get good results. If we didn't have this departure grip and we lined it up in a direct line between impact and rest, our speeds would be 25 and 58. When we move it so the tire lines match the real tire lines, we're 58 and 20. Well, the real speeds were 59.7 and 19.7. So right away, without even adjusting the friction, just using the default 0.4, we're pretty darn close. Now, the guys that did this crash originally said the post-impact drag factor was calculated to be 0.41, 0.42. And when we do that, it actually brings us to 59.6, 20.47. We're really close. But if you want to do more detailed analysis, you can click Adjust for Spin. When you do that, you then must put in the full potential of the roadway for friction. And this one was 0.55, the real one, that is. And then you're going to put in percentage braking on a wheel-by-wheel basis. And it's funny, when you do that, your results start to make a lot more sense. So putting in realistic numbers here, we're now at 0.37, 0.4. Yeah, you could argue that this number should be 10 and this one 10. And notice all the numbers changing as you do it. And our speeds have changed up a little bit, not too much. When we consult our separation velocity, it's out now, so something's wrong. So we need to make some other adjustments here, whether it's the position of the damaged centroid. So they're within 10% of each other. So you can do it two ways. You can use the built-in tire road model, or you can just estimate the post-impact friction, and you can have multiple zones. So if we go here, click Add, it puts in another zone where you can control the rotation, the position. You can even put in an instant delta V if you wanted to. And that will be factored into the overall calculation of speed immediately. So when you, at any point, you can just hit the button and it will play out. It's immediately available as a 3D simulation or animation. We want to see what damage would happen from this. Very simple. Click on SAMI. Make sure you got your right stiffness values. You can go to our website to get those. Click Damage Simulation. And in this case, the speeds are too high to allow that. So I got to go back here and delete that zone. And see how that changes our speeds, and that's better. We'll go back to SAMI. Click Process, and now it has simulated using the EDSMAC4 method, and it shows us our damage. You would match that to the real damage as a way to validate the results. So this is a really effective and useful tool with a validation paper showing that it is in fact 97% accurate with good data. Now the report is very, very detailed. It ends up being about a 25-page report when it's all done, because it outlines the entire method, all the calculations. Because we animated the vehicles, it will include an animation report. So the details of the report are really, really good and fully explain the process. So I'm not going to go through all the pages here, but this just gives you an idea on how everything is displayed. So that's our linear momentum tool. Now what we're going to do is do angular momentum. I'm just going to change our ground color so you can see the tire lines, etc. We'll just click here and an angular momentum system arrives on the scene. It can be in head-on or rear end, as long as the angles, the relative angles, are within 10 degrees, you're all set. Again, this system here should be used with vehicles out of the database. That makes sure that you've got everything correct as per specs. So we'll insert this van, and then for the second vehicle we use another manufacturer. Again, we're going to put the CG between the vehicles. We're going to use our diagram to align our vehicles. So if one vehicle ended up like that, the other one like that, to get the speeds we have to tell the system something. So in this tool you can put energy lost in, that is foot-pounds, relative velocity, velocity of 1 or the velocity of 2. You can choose. So let's just say the relative velocity was 32 miles per hour. Now when we go to details, we've got 38 and 6 as our speeds, and as I move a vehicle or adjust anything, it will always update both. Again, we can go to damage and simulate the damage. We can play this as an animation and get a very detailed report. Now, if we want to make it a head-on, let's turn it around. It recalculated the damage just about as fast as we can move things here, and it's still a valid solution. As long as they're within 10 degrees of each other on approach, it can be an offset collision. Again, under known, we could choose number 2. So if we knew number 2 was 15, it resolved everything at the same time, gave us 55 and 15. Now, as we adjust things here, recalculates vehicle 1, not vehicle 2, because vehicle 2 was known. Same thing. We can animate the results right away. The report looks much like the other report that we reviewed. Let's do something else now. So again, I'm going to change my background so you can see tire marks, and I'm going to simulate vehicles this time. So I'm going to simulate a 2-vehicle collision. I'm going to insert the one vehicle and I'm going to put it into motion. And I'm going to give it the speed that I want to start the simulation with, say 34 miles an hour. I'm going to go back to the database to get vehicle 2. So let's use a BMW 3 Series. Add the animation path. So in our system, in the reality system, you can have the vehicles in motion when the simulation kicks in. So you line them up with a little bit of space between them because this is using the original SMAC algorithms, which likes to calculate the impact point. So we're going to click Add to Simulation, click on the path of this one, Add to Simulation, and almost instantly the trajectories and the collision is modeled. So the damage to the vehicles and the trajectories are done instantly. This will work on 3D terrain. Updating, getting different iterations, very simple. If I want to change my impact angle, just do that. Immediately recalculates. And recalculates. If I go to Advanced Properties, and go to this level where I can adjust things in really tiny detail. So I can go in and it'll update as fast as I can really click. If I go to Advanced Properties, I can go in, change braking over time. So if I want to set my time increments to 1/10 of a second and adjust things here, it's going to be from that time point on. So if I say at that point there was 100% braking, right away it changes. If I click Update, there's going to be a minor change in the trajectories at that point. If I make this 100%, that means all the way through the time path, it'll be 100%. So again, we had a small change because of one wheel. We lock another wheel, changes it again. If I put in a steering input, changes it again in small amounts. So the collision is modeled very precisely based on the original SMAC method, and it all shows up in your simulation report. Thanks for watching.